Okay, we're going to look at sums of independent random variables. Just to remind you from statistics and maths, your test for independence is that if events A and B are independent, that's equivalent to the probability of A times the probability of B being equal to the probability that you're in the intersection of A and B. And this is quite key to this whole thing. You need to be a little bit careful with independence. So they're definitely independent random variables. Dice A is going to have 3 faces showing 1, 3 faces showing 2. Dice B, 2 faces showing 0, 4 faces showing 1. And outcomes on the dice are independent. And so the probability generating function for dice A is going to be a half t, so you've got a half probability of getting a 1 plus a half t squared. And then for dice B, the probability generating function, I'll call this one y instead of x. So you've got 1/3 chance of getting 0 and 2/3 chance of getting 1. So that gives you those 2 probability generating functions. If I put the probabilities into a table as well, I might have to flip between boards a little bit. So yeah, you have to bear with me. So for x, possible outcomes are 1 and 2. And the probability x equals x is a half for each. And then for dice B, possible outcomes 0 and 1, and the probability of getting 0 is 1/3 and 1 is 2/3. So that's just the probabilities written as distributions instead. We're going to let Z represent the sum of the 2 scores. So this is what we mean by the sum of independent random variables. And so Z is equal to x plus y. If I pop this into a table, so I could get a total score of 1 if I get 1 on the first dice and 0 on the second dice. That's the only possibility. And the probability of getting that is going to be half times 1/3 because they're independent events. If they weren't independent, then that wouldn't necessarily be true. So 1 on this one followed by 0 on this one, half times 1/3 is 6. You should be okay with this from the stuff you've done in statistics, but if you're not, let me know. I could get an outcome of 2. That would be a 1 on the first dice, 1 on the second. So that's a half times 2/3. Or I could get 2 on the first, 0 on the second. Sorry. Might have to write down the right probability. So 2 on the first, 0 on the second is a half times 1/3. And then that totals to give you a half. Or you could have a total outcome of 3. And the only way you're going to get that is if you have 2 on the first and 1 on the second. And that probability there is 1/3. So they all add up to 1, or something weird going on. And the probability generating function for Z is equal to 1/6 t plus a half t squared plus 1/3 t cubed. If we go back to the probability generating functions, so I'm going back to these now, then to get the probability generating function for z, you can pick up the probability generating function for x and times it by the probability generating function for y. And if you think about it, when you multiply this out, you get the probability of all your possible outcomes. So that'd be 1 followed by 0. This is 1 followed by 1, 2 followed by 0, 2 followed by 1. And because you add your powers of t, you'll then get the probability generating function for the sum of the two events x and y. And if you can multiply that out and verify that you get the above here. And so to find the probability generating function for z, you do probability generating function for x and you times by the probability generating function for y. And essentially, because when you multiply you add your powers, that then gives you the sum. And that's the bit you need to know. So I'll do an example with that as well. This is called the convolution theorem. I'm looking for a different colour pen, if I can find one. I've only got green, hopefully you can read it. Right, so that's called the convolution theorem. The proof is beyond A-level, so we're not actually proving it, but you can see that it works, hopefully, from that sense of independence. And it does extend to 3 or more variables. But again, you won't need this for your exam. So, for instance, if you had gx plus y plus z of t, then that would be probability generating function for x times probability generating function for y times, I hope you can still see that, the probability generating function for z.